So now I'm going to get into circuits. This is very, very, very basic stuff. You don't, basically, there's, all I'm going to really talk about, the only component is like this resistor. That's basically the only component I'm going to deal with. And then what some labels are. So when you, this whole process, you likely going to have to look at data sheets. And some labels of things are different depending on what kind of data sheet or what lingo, EE lingo they're using. First one, VCC VDD, or V plus 5. That means positive voltage. Hang on. VEE, I never see this one. But VSS or ground, that means typically ground. The reason why they're called that way is that ground isn't necessarily 0 volts. And that's electricity thing. But for this is ground, this is plus 5 volts. Or plus 8 volts, or plus 9 volts, or plus 10 volts. This could be minus 12 volts, I've seen that too. But yeah, don't mix these up. When you first power on your keyboard, so you finally figure out where the power and the ground are, don't swap them. If you turn on your power supply, you don't have, you plug it into your computer, there's a chance you're going to fry everything. You could fry your computer, because basically you have an open circuit that could just basically drain power. Computer shut down, or something bad could happen. Might not, but it could happen.
Probably a ground trace on your motherboard.
That's true. This is how you get fire. Yeah,
you need fire.
Yeah, you need fire. This is how you get it. PE is a neat one. Physical earth is what that stands for. So this is usually ground, but you know that like third pin you see on plugs everywhere? That's basically physical earth. Or when you have metal on your cable, it's for shielding. So often this is the same as this, but it's not necessarily. And it has to do with whatever rule of thumb that electrical board engineer was following when they're doing their work. Sometimes this matters. Like some of you saw that Chrome keyboard I had. So that is a grounding nightmare. I still to this day can't scope it because I don't know how it's supposed to be grounded. Basically it's working like an antenna. And so I'm like catching the signals from the world on my oscilloscope. So I have to figure out how they grounded it before I can actually scope it. And the reason why something like this matters is that when I want to actually measure a signal, I don't want interference from the outside world. Like I mentioned earlier, electricity is dangerous. 5 volts is harmless, basically. So I can, basically during this demo, I can touch it and do things. But things you don't want to do, hold plus, hold minus in one hand. You're doing a circuit. Okay? You don't want it to go through your heart. It doesn't take that much to actually stop your heart. Currents is very dangerous. High voltage is very dangerous. I worked on an electric car once. You work only one hand, no rings, no nothing. If you bridge 2 fingers together, it's not much is going to happen. You'll get a shock. You might get some burns. But if you go through an organ, that's a lot worse. So be careful. Ground circuits before testing, but ground loops are dangerous. So I'll try to explain in a very few number of sentences what a ground loop is. If you have 2 circuits, so if you're testing and you have a computer, make sure those plugged in the same plug. So we're going to talk about that physical earth. So it is ground or this base signal. So your base signals are 2 different buildings. So my university had this problem. They do these demos. So if you had 2 extension cords from 2 different buildings, your physical earth could actually be different voltages. They could be different in like 30 volts, 100 volts. And so when those connect, there's this loop of current that goes around, and it basically sucks all the current away, and this is how you burn down buildings. This is not like little fire, like your board goes, this is like blow up things. So yeah, be very careful. Just use one plug, and if you're dealing with keyboards, the voltages are not high enough to actually do this stuff, but if you watch like EEV blog, he will show you what happens. And it's quite entertaining, but yeah. Yeah, same circuit. Just be safe. Zapping 5 volts won't hurt you. But it's pull up, pull down resistors. So this is an interesting one. So when you have, actually I'm going to click on this link because this link is actually really good. Here's this picture. So let's say we have a switch, keyboard switch, which is great. So let's say this is a keyboard switch. And when we want to bridge, we want to sense there's something on this switch, we can apply voltage to one side. And then when we press it, if we sense that there's 5 volts on the other side, or some sort of difference, we can say it's good. Now what if it's off? You have to keep in mind is that voltage is a relative thing. It's not a defined thing. That's why you need ground. That's why there's just not, you just don't need one thing to power your light bulb or your phone or whatever. So when the switch isn't connected, say just this here, what that's called is floating in electrical engineering. Floating is don't do anything. Like it could be 5 volts, it could be 2 volts, could be anything, because basically it's measuring itself. And to the way that it's done, it just can't work. It doesn't work at all. So the way to get around that is you have to use this pull up or pull down resistor. Pull up means this is attached to a positive like voltage. Pull down usually means to either ground or negative voltage. So what this does is that when it's not connected to anything, it's detecting 5 volts. There's this resistance, but because there shouldn't be any current flowing, it doesn't waste power on it. But when it's closed, because this is a high resistance, it's not connected. It's gonna sense this right here, because the way the current flows, like the electrons flow through, it's gonna path of least resistance kind of thing. So it's gonna go through basically here instead of here. So that's the whole point of pull up, pull down resistors. And the reason why I bring it up is that on a lot of these cables, you have to deal with this problem where they assume that the pull up resistor or pull down resistor was going to be on the computer side, not on the keyboard side. And unless you actually look and trace PCB, you often don't know. I'll get into it, but the easiest thing to do is like try it without, and if it doesn't do anything, just add one. Because you basically all you have to do is figure out if it's regularly ground or 0 volts, add a pull-up resistor. If it's regularly 5 volts, add a pull-down resistor. It's literally that easy. Let's see. Try to go back. So floating, rule of thumb. Add something if it doesn't do anything. It usually won't hurt it at all. Unless you do something weird like okay. So that's basically the overview of what you need to know to actually start thinking about reverse engineering. Now you have to think about, okay, the protocol sucks. You only get press, only thing that comes out is ASCII. So you press A, it sends you an A. That's if you hold down, it might send you another A, maybe. There's no guarantee. And if you press B at the same time, it'll send you B. If you release A, nothing happens. So it literally tells you nothing. There's one key rollover. It is a piece of crap. Like why did you do this to me?
This is a USB head protocol? No,
this is not USB head.
No.
This is just a random keyboard that we're taking out. And so what I'm trying to do is map this random keyboard to USB, which is press release. So you can do it, but just give up. Just give up. I do have some examples of actually what you can do. The big problem is you can't do modifiers. That's really what needs the press release. You can't hold shift down. You can do shift. What you can do is if it sends you capital A, you can actually extract out the shift and then Shift and A. But that doesn't help you if you just need to press Shift. Or like control codes, you can actually like Control C, you can actually extract out the Control C. But what if you need to press like something that doesn't exist in ASCII? Or you need Alt. There's no Alt in ASCII or Beta or those sorts of things. That's basically why I say give up. It's like it's not really worth your time. It's a fun puzzle exercise.
There's no mapping of Alt to ASCII that people respect.
There is just doesn't exist. There's not any mapping of Shift or Control. Only some of the keys have shifted versions of themselves. Yeah. So, like I said, you can make a keyboard you can sort of use, but if you want to do anything reasonable with it, and it's only one key rollover, you can only just you can't. What I tend to do when I type is I sort of blur the next key into the next, and so I physically I do need multi-key rollover. So one key rollover doesn't really work well for me. And also, basically what you got to do is controller replacement. So there's some options there. You cut off the PCB, do the traces directly to the switches, or you can actually figure out, you can pull out the big chip, microchip, and you can sometimes put like something like teensy down if you solder the wires correctly. And then it just becomes a little bit different kind of reverse engineer exercise just to see how it's scanning and where the pins are. It's a different exercise. Technically, actually kind of simpler. It's more difficult figuring out what it does. But. So, this one's actually really cool. This is actually convertible. I could actually make a converter for this. I'm missing a gear here though. So that's like my biggest problem. This thing right here is actually a rocker switch. So when you press this key, it encodes this rocker. So when this spins, it spins this little lever here, and so it's like Morse code. So it keeps going up and down. So it encodes this little roller thing. So it'll have these 7 bits or 7 pieces of.
What's this for?
This is a teletype.
Okay.
So this was a military one, I think. But you can find the full ones of these with the printers. But this one itself is not that heavy. Like I could actually see myself carrying this into Starbucks. Just to spite people. Yes.
The lights dim as you plug it in.
Yeah. This right here is for cooling. Yeah. So someday I'll convert that. But basically, my biggest thing is I need a gear here to turn this.
Why don't you pull that missing gear off a tractor or something like that, right?
Basically, so apparently you can actually change the words per minute because there's only one key rollover. You can only press one key at a time. But the motor has different gearing speeds. So you put different gears on it. You can do like 60 words a minute. You can do 120 words a minute with this thing. Still like this, but it's 120 words a minute.
I think
You need a fan to cool it off.
Yeah, basically. So, and the big cable thing here. So, yeah, this is in my closet somewhere.
When they're sealed like that, by the way, in the military gear, they call it bomb-proof.
Bomb-proof?
So you get bomb-proof Morse code keys. They're the sealed ones.
Yeah, I have some like keyboards
that
that are.
Shove any dirt in.
Yeah, yeah. They're pretty cool. Next one, protocol sucks. Press, hold, and end key rollover, but no release. So sometimes what happens is you get the press, and it'll do repeat rate. So it'll press, and then it'll also keep telling that you've pressed it in the protocol. Totally doable. So what you can do is you can infer release by just it not happening. So if you no longer get the signal anymore from the protocol, you can just say they're no longer pressing, it's released. So it's very doable. Modifier. So sometimes this gets tricky with modifiers, but yeah, you might have some problems with the keyboard and sort of certain combinations. You wouldn't be able to map certain things, but yeah, pretty easy. Last one. So yeah, more steps. First step. Clean the keyboard, please. Because if you're gonna ask me a question, take a picture. I don't want to see like 30-year-old Cheetos. They're gross. That's not the worst thing I've seen in keyboards. Yeah,
Swamp.
I have keyboards that were pulled out of a swamp. And I know this because when I take them up, I can shake them for an hour, and dirt will still fall out of it. I cleaned out one of them. The switches had dirt inside it. Wow. And I only cleaned it because I didn't have any of these switches, so like I had to do it. And then like 2 weeks later, I got some new in-box switches. Why did I spend money? But anyways, we all know with these things. So yeah, take pictures. Specifically, if you're gonna ask me or somebody else for help, you want to take pictures of microchips. Because you want data sheets. So the more data sheets you have, the more information you have, the more easier you can make a decision on what's actually happening. And PCB traces, so you can reference what you're trying to do. Multimeter is the easiest way to do traces because you can make it beat for you. But yeah, data sheets. Sometimes you can't find data sheets. I have a Soviet keyboard around here. You're probably not going to find those data sheets, even if you had a Russian friend. But a lot of data sheets are very easy to find. There's some annoying website with lots of ads, but they will have the PDF of this really badly scanned data sheet, which will tell you this 5 volts, and that is very useful. IBM is notoriously bad because they custom order microchips with their own part numbers, so they don't map to what they actually are. So you can never look up the data sheets for these things. You have to guess. And then they also make their own custom microchips. Those are worse. But most of the IBM things are taken care of because people really want to use those, so you don't have to deal with those. So yeah, something like this. So you can see the numbers, you have pins come over. So when you look at all the pictures I take, I do a lot of pictures like these. And it's often so I can reference. I don't have to open up the keyboard again to find out what chips it's using. I still usually have to do that, but I can just reference and find them quickly.
Those are some beautiful traces.
Okay. Now we have our keyboard. Step 1. Find VCC and ground. We got to power this keyboard on without making a bonfire. So yeah, data sheets are the easiest. If the data sheet tells you it's 5 volts, you're 5 volts usually. I had one keyboard. It said all the things said 5 volts. Didn't work. Basically, it had this what's called a voltage regulator with this giant heat sink on it and this enormous resistor to take in this random ass power thing. I think it was like 12 volts or something, or 9 volts or something like along those. The keyboard would get hot because of this. It had to take this power and then convert it to 5 volts, like everything else used. So what you can do to get around that, you can often like put a cable around, just like go 5 volts directly. But generally, if you have a reference, it's way better. I mean, some IBM keyboards need a minus 12 volt. It's stupid. It's this old transistor tech that needed to weird stuff. It's not always 5 volts, but it usually is 5 volts. So, and what's good about that is you can use USB. If it's not 5 volts, you need an external adapter, and it almost will not be less than 5 volts. That's a modern thing, less than 5 volts. There are other ways to find VCC and ground. These take experience, but basically you can look at things like, is the pin connected to the case? It's probably not power. They don't want to electrocute you, probably. So that is likely a ground instead of a VCC. Things like that. There's usually more ground pins than there are voltage pins on the connector. That's usually the case, not always, but yeah. So it basically comes to toss up, and you got to basically guess. And sometimes you can usually identify VCC and ground, the two of them, because all the chips have to connect to power and ground. So you can eventually find those two pins, and then you just sort of choose which one.